A feedback mechanism is an interaction in which a perturbation or change in one climate quantity causes a change in a second, and the change in the second quantity ultimately leads to an additional change in the first. A negative feedback is one in which the initial perturbation is weakened by the changes it causes, and a positive feedback is one in which the initial perturbation is increased. Some examples of feedback mechanisms in climate change are: Number 1. Polar ice melts. As the atmosphere and oceans warm, the warmer temperatures melt the sea ice, which exposes a much darker ocean surface. This triggers a positive feedback by lowering the albedo of the ocean's surface and leading to more of the sun's light being absorbed, amplifying the warming. Number 2. A water cycle feedback. As the concentration of other greenhouse gases in the atmosphere increases, the temperature of the atmosphere warms, and so the concentration of water vapour in the atmosphere, or the absolute humidity, also rises, enhancing the greenhouse effect further. With every degree of air temperature, the atmosphere can retain around 7% more water vapour. As our carbon dioxide concentrations in the atmosphere increase, the oceans will take up more CO2 almost everywhere, but particularly in the North Atlantic and Southern Oceans. The take-up of CO2 by land areas will increase everywhere, particularly over tropical land and in humid regions where the amount of biomass is high. There is also a relatively large increase over Northern Hemisphere temperate and boreal latitudes because of the greater land area and the large area of forest. Without this increased uptake of CO2 by the land and oceans, annual increases in atmospheric carbon dioxide concentrations would be around double the observed rates. As the atmosphere warms, tropical ecosystems will store less carbon, as will mid-latitudes. At high latitudes, the amount of carbon stored on land will increase, although this may be offset by the decomposition of carbon in permafrost. As sea ice melts, more water is exposed and therefore more CO2 can be taken into the water. As the water warms, the solubility of CO2 in the water decreases and so less is taken up by the oceans. Ocean warming and circulation changes will reduce the rate of carbon taken up by the Southern Ocean and the North Atlantic. At the moment, vegetation in the Arctic is responsible for about 10% of the CO2 uptake by land globally. Permafrost soils on land and in ocean shelves contain large pools of organic carbon. If permafrost melts, microbes decompose the carbon, releasing it as CO2, or where oxygen is limited, as methane. As the climate of the Arctic warms, more permafrost will thaw. However, warmer Arctic summers would also mean an increase in the amount of vegetation and therefore photosynthesis, and CO2 uptake in the Arctic will increase. As yet, scientists don't know which process will dominate over the next few decades. To complicate matters further, the microbes decomposing the carbon also release heat, causing further melting, and that's also a positive feedback. Methane hydrates are another form of frozen carbon found in deeper soils. Changes to the temperature and pressure of permafrost soils could lead to methane, a gas with a much stronger greenhouse warming potential than carbon dioxide, being released. However, most of the methane is virtually certain to remain trapped underground and will not reach the atmosphere. The release of carbon dioxide and methane from the Arctic will provide a positive feedback to climate change, which will be more important over longer timescales, millennia or longer. As Arctic and subarctic regions warm more than the global average, the increase in temperature could lead to more regular fire damage to vegetation and soils and carbon release. More generally, increased vegetation cover lowers albedo, meaning that more of the sun's light is absorbed, which in turn warms the climate locally, another positive feedback, as well as increasing evapotranspiration and carbon uptake. It is the concentration of greenhouse gases in the atmosphere, rather than the emission at a particular moment in time, which determines the temperature of the Earth. How the concentration of carbon dioxide changes is determined by the balance between the amount of carbon dioxide going into the atmosphere and the amount being taken out. In this image, the water level in the bath represents the concentration of greenhouse gases in the atmosphere. If the emissions tap's almost closed, there is less or no carbon dioxide being added to the atmosphere than is being taken out by natural and human processes. The concentration of carbon dioxide in the atmosphere falls. If slightly more carbon dioxide is being added to the atmosphere than is being taken out by natural and human processes, the concentration of carbon dioxide in the atmosphere rises. If much more carbon dioxide is being added to the atmosphere than is being taken out by natural and human processes, the concentration of carbon dioxide in the atmosphere rises rapidly. Even if emissions fall, as was the case briefly in 2020 when COVID-19 related restrictions reduced global emissions, the concentration of greenhouse gases in the atmosphere continues to rise. Even if all emissions of greenhouse gases stopped immediately, the global temperature would still warm by a few tenths of a degree over the coming decades and centuries, because the climate system takes a while to adjust to the new conditions. Specifically, the oceans, and in particular the deep oceans, are warming more slowly than the air and will take longer to stop warming. In these figures, the orange line shows a projection of what might happen if all emissions were stopped over 50 years. When we look at projections of the future climate change, there are a lot of unknowns. 1. How are greenhouse gas emissions going to change? 2. What new technologies will emerge? For example, if nuclear fusion becomes a reality, it could have a dramatic impact on reducing our reliance on fossil fuels. 3. How will the global population change? So the best we can do is to use different scenarios to generate many projections for how the climate might change. For example, if we globally reach net zero by 2050, that means if human emissions of carbon dioxide are balanced out by how much carbon dioxide we remove from the atmosphere, we could still just keep global warming below 1.5 degrees Celsius. Projections of future climate change are made using computer-based climate models. These are the same models which are used to make daily weather forecasts. This figure shows the range of projected temperature changes with a scenario of business as usual emissions ceasing in 2300, shown in red, a scenario of aggressive emission reductions falling close to zero 50 years from now in the orange, and 2 intermediate emission scenarios in green and blue. This figure shows how carbon dioxide concentrations in the atmosphere, atmospheric temperature, and sea level responds to a peak in greenhouse gas emissions within the next 100 years. The United Nations Framework Convention on Climate Change, the UNFCCC, aims to prevent dangerous human interference with the climate system. 197 countries have ratified the convention. A conference of parties, COP, happens every year to review the national communications and emission inventories submitted by the countries or parties which have ratified the convention. Based on the information, the COP assesses the effects of the measures taken by parties and the progress made in achieving the ultimate objective of the convention. The ultimate objective is to stabilise greenhouse gas emissions at a level that would prevent dangerous anthropogenic interference with the climate system. It states that such a level should be achieved within a timeframe sufficient to allow ecosystems to adapt naturally to climate change, to ensure that food production is not threatened, and to enable economic development to proceed in a sustainable manner. The Convention puts the onus on developed countries to lead the way. The idea is that, as they are the source of the most past and current greenhouse gas emissions, industrialised countries are expected to do the most to cut emissions on home ground. These countries are called Annex I countries and belong to the Organisation for Economic Cooperation and Development, OECD. They include 12 countries with economies in transition from Central and Eastern Europe, Annex I countries were expected by the year 2000 to reduce emissions to 1990 levels. The Convention directs new funds to climate change activities in developing countries. Industrialised nations agree under the Convention to support climate change activities in developing countries by providing financial support for action on climate change, above and beyond any financial assistance they already provide to these countries. A system of grants and loans has been set up through the Convention. Industrialised countries also agree to share technology with less advanced nations. Industrial countries, Annex I, have to report regularly to the UNFCCC on their climate change policies and measures. They must also submit an annual inventory of their greenhouse gas emissions, including data for their base year, 1990, and all the years since. Developing countries or non-Annex I parties report in more general terms on their actions, both to address climate change and to adapt to its impact, but less regularly than Annex I parties do. And their reporting is contingent on their getting funding for the preparations of these reports, particularly in the case of the least developed countries. Economic development is particularly vital to the world's poorer countries. Such progress is difficult to achieve even without the complications added by climate change. The Convention takes this into consideration by accepting that the share of greenhouse gas emissions produced by developing nations will grow in the coming years. Nonetheless, in the interest of fulfilling its ultimate goal, it seeks to help such countries limit emissions in ways that will not hinder their economic progress. The Convention acknowledges the vulnerability of all countries to effects of climate change and calls for special efforts to ease the consequences, especially in developing countries, which lack the resources to do so on their own. In the early years of the Convention, adaptation received less attention than mitigations, as parties wanted more certainty on impacts and vulnerability to climate change. When the IPCC's third assessment report was released, adaptation gained traction, and parties agreed on a process to address adverse effects and establish funding arrangements for adaptation. In 2015, at COP21 in Paris, all parties adopted the Paris Agreement to limit global warming to less than 2 degrees Celsius and pursue efforts to limit it to 1.5 degrees Celsius. This graph shows historical global emissions of greenhouse gases in black and how they will change if policies that countries already have in place are complied with in red, how they would change if countries comply with the promises they have made in the dashed bar, and how they need to change if we are to keep within 1.5 degrees Celsius warming in blue or 2 degrees warming in green. A globally average climate change like 1.5 degrees doesn't sound a lot, but it's important to remember that it can mean local and short-term changes that are far greater. We've already seen that the Arctic and land areas warm more than the air over the oceans. The hottest day temperature rises faster than the average, which of course is very significant for heat waves. Future climate change is projected to increase the severity of impacts across natural and human systems and will increase regional differences. A climate tipping point is a critical threshold when global or regional climate changes from one stable state to another stable state. The tipping point event may or may not be irreversible. For more information on tipping points, go to Chapter 15.